Hello all, welcome to the next lecture. In this lecture, we'll go into the topic of biomolecules starting with carbohydrates. So in this lecture, we'll discuss carbohydrates, Fischer projections of monosaccharides, Haber structures, chemical properties, disaccharides and polysaccharides. So let's start with the core chemistry skills that you need for this lecture. So before going into this lecture, review these following topics. First, about naming alcohols and phenols. Second, writing the equations for the oxidation of alcohols. And third, how to name aldehydes and ketones. So let's get into the lecture. So let's start with carbohydrates. So carbohydrates are the major source of energy from our diet. Most other elements that you generally eat need a lot more time to digest, but carbohydrates are the ones that provide you readily available and easy form of energy to be converted into regular source of energy. So these are generally made from elements of carbon, hydrogen and oxygen. So the other name for carbohydrates are also called saccharides, which generally means sugars. Now, the goal here in this section is to classify a monosaccharide either as an aldose or a ketose and indicate the number of carbon atoms that the sugar has. Now, carbohydrates generally such as glucose are produced by photosynthesis in plants. So they are synthesized by plants by consuming carbon dioxide and water and energy from the sun, and are oxidized in living cells to produce carbon dioxide, hydrogen, water and energy. So the photosynthesis is the opposite of respiration. In photosynthesis, we take carbon dioxide, water and energy and we convert it into glucose. For respiration, we use glucose and oxygen and release carbon dioxide and water. So what are the types of carbohydrates? So we simply classify them into three types. One is monosaccharides, the simplest of carbohydrates. You have disaccharides, which are ones that contain two different attachments of monosaccharides. Polysaccharides are the ones that contain many monosaccharides. An example of a monosaccharide is honey. Honey contains fructose and glucose. Each of them are monosaccharides. Now, under hydrolysis, monosaccharides generally do not undergo hydrolysis because they already are a single individual substances. Now, milk is an example of a substance that is a disaccharide. So the common name is lactose. And lactose is a disaccharide. Under hydrolysis, it splits into two monosaccharides. Now, you have polysaccharides. For example, cotton consists of polysaccharidic cellulose. And these polysaccharides are long chain monosaccharides that under hydrolysis also do the same thing, either under hydrolysis or in the presence of an enzyme. They split into individual monosaccharides. Now, these monosaccharides contain several hydroxyl groups attached to a chain of 3 to 8 atoms. Now, the ones that contain the aldehyde group are specified as aldoses, and the one that contains the ketone groups are called as ketoses. Now, they have hydroxyl groups on all the carbons except for the carbonyl carbon. So the carbonyl carbon is the one that contains either the ketone group or the aldehyde group. For example, if you look at this structure here, this is a aldehyde structure. So this is an example of an aldose. The name of this sugar is erythrose. So this is an example of a sugar that is containing a ketone group. So it is called as a ketose. So the names are aldose and ketose. Remember, this one is O's represents that it's a sugar. Now, monosaccharides can also be classified by the number of carbon atoms that they have. If they have 3 carbon atoms, we call them trioses. If they have 5, pentose. If they have 4, tetrose. If they have 6, hexose. Now, so if you see a structure that is named as aldopentose, so pentose represents that it's a 5-membered saccharide, 5-carbon saccharide, and aldo represents that it has an aldehyde group. And a ketohexose is a 6-carbon saccharide that contains a ketone group. So this is how we generally classify monosaccharides. For example, the triose, aldotriose, is the other name for aldotriose is glyceraldehyde. So this is the structure. Notice the aldehyde group on top. So notice the aldehyde group here. Now this is aldotetrose because it has 4 carbons and an aldehyde group. Here again, it has an aldehyde group, so aldo, and it has 5 carbons, so it becomes pentose. So the name is aldopentose. So fructose is a ketohexose where you have a ketone group and you have 6 carbons. So this is an example of a ketohexose. So use the principle now and try to name the following structures. So pause the video right here and try to solve this problem. So as you see here, so the first one contains an aldehyde group and it has 6 carbons. So it becomes an aldohexose. And here you have 5 carbons and you have a ketone group, so it becomes a ketopentose. Now, what are the main ways to represent a monosaccharides is most commonly by using Fischer projections. So mostly glucose, galactose, fructose are the most common and most important monosaccharides. And in this section, we'll learn to identify and draw the D or L configuration of Fischer projections for common monosaccharides. So remember that they are isomers and the isomers can be represented by using the D or L method. So DL classification is a part of classifying monosaccharides in the basis on their Fischer projection. So the first thing that we need to do is we take the sugar structure and turn it clockwise by 90 degrees. Now when you turn it clockwise by 90 degrees, we are always noting down the carbon numbering from the carbon that contains the carbonyl group. So here it's an aldohexose, so it becomes from there. Now we know already the Fischer projection, so it's a common way to represent carbohydrates. So we place the aldehyde groups at the top and we show the hydrogen and the OH groups on the horizontal intersecting the line. So placing the achiral CH2OH at the bottom. Notice that each intersection point here represents that is a chiral carbon. So any achiral carbons are generally written as carbons directly. Now this is the question, what is D and what is L here? Now if the OH group is on the left side, we call that a L-glyceraldehyde. Now this OH group is the one that's closest to the achiral CH2OH. So the achiral CH2OH is the one that decides whether it is D or L. Now if it's to the left, then we call it L-glyceraldehyde. If it's to the right, we call it D-glyceraldehyde. So this is how we can classify of using Fischer projections. So in the Fischer projection, the OH group on the chiral carbon farthest from the carbonyl group determines whether it's an L or D isomer. So the left one is assigned as the L, so assigned the letter L, and the right one is assigned the letter D. So most commonly the reason it becomes L and D and not L and R is because the name comes from the fact that it is levorotatory. So levorotary and the term dextrorotary. So which represent that it is left and right. So this is the reason why we use L and D. So here, how would you, for this glucose, how would you do that? For example, we are looking at the one that is farthest from the carbonyl carbon. The farthest one is this carbon. So this carbon on this side, OH group is on the left side, so it is L glucose. Here the OH group is on the right side, so we call it D glucose. So this is how we can classify the monosaccharides. So most important of these monosaccharides are D-glucose, D-galactose and D-fructose. The only way you can differentiate them is the arrangement of OH and H groups on the achiral carbons. So that is how we can classify hexoses into different types. So these are all hexoses, they all have the same molecular formula, but they are all isomers of each other. Now what is the most important one? The first important one is D-glucose. It is the most common hexose. This is the one that is found in fruits, vegetables, corn syrup and honey. And it's also known as dextrose and blood sugar in the body. So this is the building block of disaccharides, so sucrose and lactose, and of polysaccharides such as cellulose and glycogen. So D-galactose is an aldohexose with the same molecular formula, but most commonly it is obtained as a disaccharide of lactose in milk, and it is the most important one in the cellular membranes of the brain and the nervous system. So there is a condition called galactosemia where the enzyme that is needed to convert D-galactose to D-glucose is generally missing. So in that case, the galactose here accumulates in the blood and the tissue, which can lead to cataracts, mental retardation, failure to thrive and liver disease. So these are some of the most important factors for group fructose. Next one is D-fructose. D-fructose is a ketohexose with the formula of C6H12O6, and it is the sweetest of all the sugars. It is twice as sweet as sucrose, the table sugar, and it is mostly obtained as one of the hydrolysis products of sucrose. And one of the most common ones that you generally see is HFCS, which is high fructose corn syrup. This is the common sweetener that is used in the US to make soda beverages, and it's the sweetener that is produced by making down enzyme to break sucrose to glucose and fructose. So now let's try and identify whether a given monosaccharide is a D or a L isomer. So the step one is to number the carbon chain starting from the top of the Fischer projection. And step two is to locate the chiral carbon that is farthest from the top of the Fischer projection. And step three is to identify the position of the OH group as either D or L. Now for this structure here, first thing that we need to do is number them. So the numbering is 1, 2, 3 and 4. So the chiral carbons are the ones that is chiral carbon is the one that is farthest from the group here. The chiral carbon that is farthest from the group here is this carbon here. Now this carbon here on the OH group here is on the right side. We can say that this is a D. They already given you this name, so we can write it as ribulose. So this is how we can name the compound. So one of the most common conditions that is linked to your health is conditions called hyperglycemia and hypoglycemia. In the body, your glucose has a normal blood level of 70 to 90. So a glucose tolerance test is generally the one that is used to measure the blood glucose for several hours after ingesting glucose. Now, if the sugar is less than normal, we call it hypoglycemia, and if sugar is more than normal, you enter a state called hyperglycemia. So the most common condition that you generally know of hyperglycemia is diabetes mellitus. This is the disease that can cause hyperglycemia. So this is a syndrome that can cause hyperglycemia, and this occurs when the pancreas here is unable to produce sufficient quantities of insulin, because your insulin is the one that regulates the amount of blood sugar in your body. So this can create a situation where the glucose levels in the body can rise to as high as 350 milligrams per deciliter, which can cause symptoms like thirst and excessive urination, increased appetite and weight loss. In older adults, the most common symptom is sometimes a consequence of excessive weight gain. So when a person is hypoglycemic, where he does not have enough blood sugar, then the blood glucose level rises and decreases rapidly to the levels as low as 40. So this can cause an overproduction of insulin this can be caused by the overproduction of insulin by pancreas. And most common symptoms are dizziness, general weakness and muscle tremors. And most commonly a diet is prescribed that consists of several small meals, high in protein and low in carbohydrates. Because the reason why you do this is because to reduce the amount of insulin that is produced, as well as to reduce the amount of sugar that is being converted into glycogen. So most common way to judge this is by using glucose testing. So most commonly blood glucose flows through the kidney and the kidneys and is reabsorbed into the bloodstream. But when your blood glucose level exceeds about 160, then the kidneys cannot reabsorb all of the glucose and it spills over. We call that condition glucoseuria, where it spills over the excessive glucose into the urine, which can cause excessive conditions, which is commonly tested by a di-O-methyladenine, which can determine the blood glucose level in urine. Now, a symptom of diabetes mellitus is a high level of glucose in the urine. So most commonly it's observed by using the Benedict's test. So this is the table that shows you the glucose oxidase test results. So depending on the color of the urine and the percentage of glucose that is present in the urine. So the higher the glucose level, the higher the chances that you have a situation of hypoglycemia. So use the principles now that we learned about Fischer projection. So pause the video right here and try to identify whether it is a D or a L isomer and try to name the compound as well. Next, let's talk about Haworth structures of monosaccharides. So the most stable form of pentose and hexose sugars are the commonly known as 5 or 6 membered atom rings, and these are called as Haworth structures. These are produced from the reaction of a carbonyl group and a hydroxyl group in the same molecule. So what happens here is that the carbonyl group and the hydroxyl group bond to each other and create a double bonded oxygen atom. This can create the cyclic structure. So how do you draw Haworth projections? First, we turn the Fischer projection clockwise by 90 degrees so that the hydrogen groups and the OH groups to the right of the vertical carbon chain are below the horizontal carbon chain. So this is the idea first. Now, the next one is left of the open chain are above the horizontal carbon chain. So remember that this here, the one that is on the left goes on the top, the one that is on the right goes on the bottom. So this is how we rotate the structure. Now once we rotate the structure, the second thing that we need to do is to make sure that we bend the structure in such a way that we keep the structure sane until carbon 4 and we keep the structure same until carbon 3 and we bend from carbon 4. So we bend at carbon 4, and what we do here is when we bend, we have to remember that we are bending it clockwise. So which means that you are going to rotate the groups on carbon 5. So specifically only on carbon 5. Once you rotate the groups now, you have to make sure that the CH2OH is to the right side, H is on the CH2OH is on the right side. So this is how you rotate the structure. Now once you have rotated the structure, you will have CH2OH on the top and OH on the right side. Now once you have rotated it successfully, next remove the hydrogen. So remove the hydrogen here and bond it with the oxygen here. This creates the final cyclic hemiacetal structure. So let me show you in an exact diagram so that you understand it better. So this is the structure that we want to do. First thing we need to do is to rotate it by 90 degrees. So we rotate it by 90 degrees. So when you rotate it by 90 degrees, remember that so you have CH2OH, next on the other side we have C double bond OH, hydrogen, OH, hydrogen, hydrogen, and in the bottom we have OH, H, OH, OH. Remember that this is the one that decides whether it is D or L. So remember, focus on that oxygen. So the next thing that we want to do is to keep the structure the same until 1, 2, and 3, and we push the 4th carbon up. So first thing that we do here, so the next thing that we want to do after you do this is to second thing is to lift the 1 up and then rotate it across the 4th carbon. So lift the 1 a little up. So we have to make sure that we bend it a little up in this direction. So basically remember that if it's a 6-membered ring, you're going to get a hexagonal structure in an aldopentose. Now how would you write down this structure here? So this becomes C double bond OH, and on this we have the second one stays the same, hydrogen and OH, and here also things stay the same, OH and H, and on the 4th carbon also everything stays the same. So we have OH and H, and on the 5th carbon also, first things first, let it be the same, and lastly write down CH2OH. Now to make sure that the bond here is between this OH and this H here, so what we do here, so we rotate it in such a way that OH goes to the right, H comes here, so we rotate it anti-clockwise. So OH goes here, CH2 goes here, and hydrogen comes to the left. So when you rotate it such a way, what will happen to the structure now? So the only thing that changes here is that the CH2OH will come to the top, the OH will come to here, and H will go to the bottom. And you have C, H, double bond O, and everything else stays the same, HOH, HOH, HOH. So this oxygen will bond with the carbon, and the hydrogen and hydrogen will leave, so resulting in the formation of the complex structure that you end up with. So what will happen here is that one of the hydrogens, that is with this carbon, it goes to this oxygen here, so resulting in the formation of an OH, and this hydrogen will come down to this carbon at the bottom. So this creates the OH side. So how will it create that structure? So let me copy this one. So that bond will end up creating this structure where OH will be on the top, OH will be on the top, and H will come on the bottom. So this is the arrangement that you will generally see. So when you number the carbons, you have 1, 2, 3, 4, 5, and 6. So this is how you can number the carbons, so resulting in the Haworth projections. Now, how do you, so using the Haworth projections also we can classify the structure as what we call anomers. Anomers are based on which side is the OH group presented at the carbonyl carbon originally. So at the carbonyl carbon, we call that carbon the anomeric carbon, which is the one that bonds. Now, if the OH group is on the bottom, we call that an alpha anomer. If the OH group is on the top, we call that a beta anomer. So this is important because this can also help you in separating the structures into two different parts. So you have alpha D glucose and you can get beta D glucose. So these are the two ways we can classify these structures. So when placed in a solution, what will happen is that these cyclic structures will become open and close. So this opening and closing is what we differentiate. So what will happen here is that the alpha D glucose will convert to beta D glucose and vice versa. And at any time, only a small amount of open chain will form, resulting in the structure formation. There will not be open structure at all. There will always be a cyclic structure present inside the structure. So this is these are the two structures of the galactose, which is an aldohexose, and it differs from glucose only in the structure that on the fourth carbon, the OH is actually on the top and H is on the bottom. So this is the only way it differs from glucose and glucose here. Fructose here is a ketohexose. It generally forms a 5-atom ring, so containing a carbon with carbon 2, so with the carbon 2 at the right corner of the ring. So remember that the carbon 2 is at the right corner and carbon 5 is at the left corner. So this is how we can differentiate. Now, so what is the guide to drawing the Haworth projections? First step is to turn the Fischer projection by clockwise by 90 degrees. Second is to fix the horizontal carbon chain into a hexagon and rotate the groups on carbon 5 so that the bond O on the carbon 5 will bond to the carbon 1. Step 3 is to draw the new OH bond of carbon 1 below the ring to give it the alpha anomer and the above the ring to give the beta anomer. So you can get both isomers at the same time. So pause the video right here and try to draw the cyclic forms of D-galactose. So next, let's talk about the chemical properties of monosaccharides. So what are some of the chemical properties of monosaccharides? So sugar alcohols, so most common ones are D-sorbitol, D-xylitol and D-xylose, and D-mannitol from D-mannose are generally used as sweeteners in many sugar-free products such as diet drinks, sugarless gum, as well as products for people with diabetes. So this is the structure. Adding hydrogen to it, hydrogenation will create do-glucitol or D-sorbitol. This is something that you can see in gum, sugarless gums, sweeteners, artificial sweeteners. These are some things that can be used in place of sugars themselves. Now, monosaccharides in general can be found as many cyclic forms in solutions. They have small amounts of open chain form present. So having an aldehyde group with an adjacent hydroxyl group can be oxidized to carboxylic acid to an oxidizing agent such as Benedict solution. So the glucose under oxidation creates gluconic acid, releasing hydrogen peroxide. This is one of the mechanisms by which your body reacts to excess sugar. Right? So sugar acids are produced from oxidation of aldehyde and reduce as COP-Cu2 plus and reduce it to Cu plus. So we basically replace O's with onic acid. So glucose becomes gluconic acid. So this is how we can talk about oxidation. So the fructose here is a ketohexose. It contains a ketone group which generally cannot be oxidized, but it can be oxidized in a basic Benedict solution when a rearrangement occurs between the ketone group of the carbon 2 and the hydroxyl group on the carbon 1. So what happens then? It converts to glucose, which is an aldehyde, and then it further undergoes the formation of gluconic acid. So first, glucose here has to undergo rearrangement to form fructose here has to undergo rearrangement to form glucose, and then undergoes oxidation to create gluconic acid. Now the reduction of carbonyl groups in monosaccharides, they generally convert an aldehyde group to an alcohol producing sugar alcohols. We call them alditols. So when you use glucose and when you add hydrogen to it under reduction reaction, it creates D-glucitol or D-sorbitol. So these are what we call alditols. So alditols are the common basic sugar alcohols. So they are basically we replace O's with etol. So glucose becomes glucitol. So they are commonly included as sorbitol, xylitol, xylose, dimannitol. So for example, D-sorbitol is already the common name for glucitol. D-xylitol is found from D-xylose. Dimannitol is generally found from D-mannose. These are used as sweeteners in many sugar-free products such as drinks, diet drinks and gums. So use the reaction now. So pause the video right here and try to write down this reaction. What will happen here? Notice what is the only change in the reaction here. You're basically adding CH2OH on both ends here. That's the only thing that you're doing here. So basically this becomes CH2OH. So let's next talk about disaccharides. So disaccharides are combined forms of sugar. So where you have two different sugar groups, monosaccharides combined to form a disaccharide. So for example, lactose is a disaccharide that is found in milk and milk products. So it contains two monosaccharides. The two monosaccharides are galactose and glucose. So this is the structure. So the ones that are present there is beta D galactose and alpha D glucose. So these are the two structures that are present in lactose. The combined form creates a bond called a glycosidic bond. So the glycosidic bond is the bond that bonds two different sugar groups. So here the bond is between the first carbon on the first sugar and the fourth carbon on the second sugar, and the alpha or beta represented by the fourth carbon. So it's going from 1 to 4 and the bond is facing downward because beta represents the downward part here. So which represents the idea that this is a beta 1 to 4 glycosidic bond. Now a disaccharide consists of two monosaccharides that are linked together, and it is generally formed by two monosaccharides combined in dehydration reaction. So you have glucose and glucose combined create maltose, which is H2O. Glucose and galactose create lactose. Glucose and fructose create sucrose. So these are the most common disaccharides: maltose, lactose and sucrose. So let's talk about maltose. Maltose is a disaccharide known also as malt sugar, and it composes of two D-glucose molecules, and it is generally obtained by the hydrolysis of starch. Most commonly it's used in cereals, candies and brewing. It's generally found in both alpha and beta forms. So what happens here is maltose here is linked by an alpha 1,4 glycosidic bond. So notice that the bond here is 1,4 glycosidic bond. This bond here is what bonds the two structures together to create alpha maltose. Next, lactose is a disaccharide found in milk and milk products. It makes up about 6 to 8% of human milk and 4 to 5% of cow's milk. So lactose is a disaccharide of two sugars, beta D glucose and alpha or beta glucose. So the bond in lactose is beta 1 to 4 glycosidic bond, because the carbon on the OH group on carbon 1 and the beta galactose forms a glycosidic bond with the OH group on the carbon 4 of D glucose. So this is what creates. So the bond in lactose, remember, is beta 1 to 4 glycosidic bond. In alpha, in the same in maltose as well. Sucrose is generally referred to as table sugar. It contains alpha D glucose and beta D fructose. Here it has an alpha beta 1 to 2 glycosidic bond. So between the carbon 1 of glucose and carbon 2 of fructose. So this is what creates. So this bond is alpha beta 1 2 glycosidic bond. Now sucrose is, it cannot form an open chain or undergo oxidation. It generally reacts with Benedict reagent and it's not a reducing sugar. So this is the most common sugar that we found that we use. We call it table sugar or cane sugar. So most of the sucrose for table sugars comes from sugar cane, which is about 20% by mass, or sugar beets, which is about 15% by mass. Now these are commonly the general sugars. There are also what we call artificial sweeteners. The artificial sweeteners are the only ones that differ in sweeteners, and they are composed of sucrose, which so they are compared to sucrose. How do you compare them to sucrose? For example, monosaccharides are generally the ones that you see here are galactose and glucose are generally less sweet than sucrose. Fructose is a little bit higher sweetness than sucrose, but disaccharides, sucrose is the highest. Maltose and lactose are really less sweet than comparison to sucrose. The same with sugar alcohols, they have similarity to sucrose. Artificial sweeteners are generally non-carbohydratic substances. These are substances that have high relative sweetness in comparison to sucrose. For example, aspartame, saccharin, sucralose and neotame. These are substances that are used as artificial sweeteners, which have relatively high sweetness factor, and this is one of the ones that is commonly used in sweetening flavored drinks, and these are also the common sugars that are used in processed foods. For example, most commonly it's used for diabetic patients, but people these days, manufacturers, because of their relative sweetness, they generally use it for many purposes, most commonly for flavored drinks. For example, things like Tang. The flavor that is bought is generally from either aspartame or saccharin. Artificial sweeteners are sucralose, saccharin and aspartame. These are the artificial sweeteners. So sucralose here is, the only difference here is basically a sucrose, but in place of OH, it is replaced with a chlorine on the second part of the carbon, so resulting in the formation of sucralose. And it is marketed as Splenda, and this is generally made from sucrose by replacing some of the hydroxyl groups with a chlorine. Now the second one is aspartame, so which has some caloric value, and it's marketed as NutraSweet or equal, and it's a non-carbohydrate sweetener made from aspartic acid and methyl ester of amino acid phenylalanine. So it's so sweet that you only need a really small quantity for it to be generally taken in. Next one is neotame. Neotame is a modification of aspartame structure. The only difference here is that we add a large alkyl group to the amine group, so which prevents it from the enzymes breaking the amide bond between the aspartic acid and the phenylalanine, so that phenylalanine is not produced, because some chances are there that phenylalanine might be dangerous towards some people, and is generally very sweet. Only small amounts of neotame are needed because it's about 10,000 times sweeter than sucrose. The next one is saccharin. It's also another artificial sweetener. This is the structure of saccharin. In market, it is marketed as sweet and low, and it has been used as a non-carbohydrate artificial sweetener for more than about 60 years. And it has been banned in Canada because the studies indicate that it might cause bladder cancers, but it's not been approved in the US. It's still approved as in the US by the FDA for use in the United States. So use the idea what you have learned now. So pause the video right here and try to answer these questions. Next, let's talk about blood types and carbohydrates. the blood types here of A, B, AB and O are generally determined by the terminal saccharides that are attached to the surface of the red blood cells, and these are unique for each blood type, and for each blood type the only thing that differs is a certain structure that exactly differentiates. For example, the base structure in all of O, A and B are exactly the same. So they all have the same exact base structures of N-acetyl glucosamine, fucose and galactose. The only differentiation is that in type O there is no acetyl galactosamine or an extra galactose, but in type A you find N-acetyl galactosamine. In type B you find an extra group of galactose. So this is how we differentiate the structures. So O has three common terminal monosaccharides, N-acetyl glucosamine, galactose and fructose. A contains the same three monosaccharides, but in addition you have a molecule of N-acetyl galactosamine that is attached to the galactose in the saccharide chain. And in the B group it contains the same three monosaccharides. In addition you have a second molecule of galactose that is attached to the saccharide chain. In AB group it contains the same molecules found in both blood types A and B. So it has both the common structures that are present in both A and B. Now the structure of monosaccharides, N-acetyl glucosamine, galactose and fucose are the structures that are given below. So these are the structures that differentiate your blood groups. So that's the reason why a person with a type O blood group can produce antibodies against blood types AB and AB. And blood type AB and AB can receive type O blood. But type AB blood, which contains all the terminal monosaccharides, produce no antibodies to all of these blood types. That's why type AB groups are generally called as universal recipients. Type O groups are called as universal donors. So this is the compatibility chart that tells you which blood group can donate blood to which blood groups. So use the principle right now, what you have learned. So pause the video right here and try to solve this problem. Next, the last topic, polysaccharides. So polysaccharide cellulose is basically composed of glucose units connected by beta 1 to 4 glycosidic bonds. So alpha 1 to 4 glycosidic bonds is called as amylose, and beta 1 to 4 glycosidic bond is called as cellulose. So polysaccharides are formed when you have many monosaccharides that are joined together. These are compounds that include amylose, amylopectin, cellulose, glycogen, which are polymers of D-glucose and differ by branching and the type of glycosidic bond. So let's start with starch. So starch is the common storage form of glucose in plants, and it is found as insoluble granules in rice, wheat, potatoes, beans and cereals. They have two types. One is amylose, the next one is amylopectin. Amylose are generally bonded by alpha 1 to 4 glycosidic bond. Amylopectin is also bonded by the same bond, but the amylopectin contains multiple bonds. It also has an extra bond of alpha 1 to 6 glycosidic bonds. So it contains two types of bonds here. So amylopectin makes up of 80% of the starch, and it's a branched chain polysaccharide, and it generally contains glucose molecules connected by alpha 1 to 6 and alpha 1 to 4. And starch in general hydrolyzes easily in water and acid to give smaller saccharides called as dextrins, and which are generally then to hydrolyze maltose and finally convert it into glucose. So you start with amylopectin. So the enzyme amylase splits it to form dextrins, and the amylase again splits it into maltose. Under maltase, the enzyme splits it into many glucose units. So in our bodies, these complex carbohydrates are digested by the enzymes amylase, which is generally found in saliva, and maltase is generally found in the intestines. So these provide about 50% of the nutritional calories from glucose obtained in digestion. The next one is glycogen. Glycogen is a polymer of glucose that is stored in the liver and the muscle of animals, and it is hydrolyzed in our cells at the rate that maintains the blood glucose level and provides the energy between the meals. So the structure is similar to amylopectin, but it's more highly branched. So the glucose units in glycogen have alpha 1 to 4 glycosidic bonds with branches attached by alpha 1 to 6 glycosidic bonds, and that occurs every 10 to 15 glucose units. This is the way your liver stores energy. right? So this is how insulin controls your blood sugar by converting glucose into glycogen. And the last one is cellulose. Cellulose is the major structural unit of wood and plants, and it's a polysaccharide of glucose units. But the only difference here is that it has beta 1 to 4 glycosidic bonds. Cellulose is really hard structure, so it cannot form hydrogen bonds with water, and it makes it insoluble in water. And it gives a rigid structure to the cell walls and in wood and fiber. And it is also more resistant to hydrolysis than starches. And it cannot be digested by humans because humans cannot break down beta 1 to 4 glycosidic bonds. So most commonly found in cotton, most commonly found in trees. Anything that's in the nature is generally how the glycosidic bonds are present. So pause the video right here and try to determine which type of polysaccharide and which type of bonds are present here in both of these diagrams. So with that, we end our lecture on carbohydrates. So this is the concept map of what we have discussed in this lecture today. So I'll see you again in the next lecture.